something called a Lagrange error bound. It's very similar to our alternating series error, right? So with the alternating series, if it's a converging alternating series, you know that there's a bound on your error, right? So if you add up the first 20 terms of an alternating convergent series, that's not going to be the exact sum, but we know the maximum value of the error will always be less than what value if it's the first 20 terms. Where do we look for the error? The next term. Which term would that be in that case? The 21st term, right? If you add up the first 10 terms, you look at the 11th term, right? And that's the maximum value that your error will be, right? It will have to be less than that. Well, the same thing works with Taylor polynomials, and we're going to look at an example of that. Because a Taylor polynomial, we'll review what a Taylor polynomial is, because that was last Friday. And with a Taylor polynomial, remember you're doing a bunch of different terms with the definition right here of a Taylor polynomial, and you could do a Taylor polynomial for sine, and you can do it up to the 3rd degree polynomial, right? And then you can do it up to the 4th degree, and the 5th degree, and the 6th degree. Let's say you only do it up to the 4th degree, and then you want to approximate a value using that Taylor polynomial. Like you want to do sine of 0.1. Okay, if you plug 0.1 into that Taylor polynomial, it will give you approximation for sine of 0.1, but it's not going to be perfect, right? The more terms you add on, the more accurate it will be. And with the same situation as the alternating series, if you do a 4th degree Taylor polynomial, the error will be whatever the 5th term is. Okay, if you do a 6th degree Taylor polynomial, the error will be whatever the 7th term is. It will be bound by that. Now, there is a little weird thing that the value we plug into the derivative, it will not be exactly that next term, but it's going to be some z value in our interval. So we usually can't actually find the exact error, so we bound it. We bound it by the maximum of whatever that is. And that's the only weird part about this, and I'm going to show you a few different examples. And when you find the maximum value of that next term's derivative, you'll do it one of 3 ways. Maybe they'll give you a graph, and you'll look at the graph for the maximum. 2, a lot of times, if it's sine or cosine, we already know the bound of sine and cosine. What's the maximum value of sine and cosine? 1. So then you know about a maximum. And then sometimes they might actually tell you the maximum value. And they say, hey, this 5th derivative is always less than 2.7, right? And then you can use that, okay? So it'll make a little more sense when we do a couple of examples here. Okay. So let's first review what a Taylor polynomial is. So we're going to write a Taylor polynomial for sine. We're going to do a 3rd degree Taylor polynomial. That's what this P3 is. So we'll go up to until our terms of degree 3. And remember from the other day, a Taylor polynomial, you always start with your function and you plug in the center. And then you do the first derivative and plug in the center. And you do x minus the center for the linear term, the x term. And then for the 2nd degree term, you do the 2nd derivative at the center, divided by 2 factorial times x minus c squared. And then repeat the pattern for each term, right? So the next term would be the 3rd derivative over 3 factorial x minus c to the 3rd degree. So we're going to use, for ours, f of x is sine, right? That's the function that we're writing our Taylor approximation for, and we're going to do it centered at 0. So we will need to first find what sine is, what our function is at 0. So what is sine of 0? 0. Sorry. It's one or the other usually. Now we're going to need if we're going to go to the 3rd degree, we're going to have to go to the 3rd term, right? So how many derivatives am I going to need? I'm going to need f. I'm going to need the 1st derivative, 2nd derivative, and if I want to go to the 3rd degree term, how high will I have to go for derivatives? The 2nd degree term has the 2nd derivative, so what will the 3rd degree term have? The 3rd derivative. So you need to go all the way up to the 3rd derivative, plugging in the center. So I want you to find the the first derivative is 0, second derivative is 0, and third derivative is 0. Go ahead and do that. You can kind of just do it up here in this little spot. Find the first derivative at 0, second derivative at 0, third derivative at 0. All right, if f is sine, what's the first derivative? Cosine, and what's cosine of 0? 1. And what will the second derivative be then? Negative sine. What's negative sine at 0? 0. And then we need to go to the third. So what's the third derivative then? Negative cosine. What will be negative cosine at 0? Negative 1. And why were we plugging in 0 to all of these? Why 0? Because that's a center, right? That's what you're plugging in to all of those. So now we're going to take those and write our Taylor polynomial with those values, right? So first term is always just the function at the center. So what was our function at the center? 0. Next term is the first derivative. What was our first derivative at the center? 1 times x minus the center, which for us is 0. Second term is second derivative. What was our second derivative? 0 over 2 factorial times x minus the center squared. And we need to go to degree 3, so we need to go one more. What was our third derivative? Negative 1 over 3 factorial x minus the center cubed. So we can simplify this down because a bunch of the terms go away. So that'll just be x minus 1 over 6, because 3 factorial is 3 times 2 times 1, x cubed. So finding a Taylor polynomial is very easy, right? You literally just find the derivative and you just follow the pattern, okay? So that's just review of what we talked about on Friday last week. So now we're going to use this Taylor polynomial to approximate sine of 0.1. So we're going to plug, so we want to approximate because this Taylor polynomial is approximating sine. So to find an approximation for sine of 0.1, we'll plug 0.1 into our third degree Taylor polynomial. So if you plug 0.1 in here, I'll just tell you what you get. You get 0.09983 repeating. So that's an approximation for sine of 0.1. Now, is that the perfect value of sine of 0.1? No. And the error will be bound by this Lagrange error bound, right? So whatever error, it will be bound by this fourth term, like Lagrange error bound thingy we get, okay? So now we're going to talk about how we find that. So R3, our remainder here, for a third degree Taylor polynomial, is bound by this Lagrange error bound, okay? And basically, you're still looking at, like, the next term, right? So since we did a third degree Taylor polynomial, what term will we be looking at? Not the third, the fourth term, because we did 3 degrees, right? So our Lagrange error bound is going to be based off of that fourth term. But we don't know what the exact derivative is at the fourth, so we're going to find the maximum of the fourth derivative at this random value z. And this z value is somewhere in a range. For this problem, z is going to be between 0.1 and 0, because our center is at 0 and we're approximating at 0.1. So that z could be any value in that region of 0 to 0.1, where we're approximating and where we centered our polynomial, okay? So we're going to need to find the maximum of the fourth derivative for any value z in that interval. That'll be divided by 4 factorial x minus the center to the 4th power. So do you see how this is basically the fourth term, except you're finding the maximum of the fourth derivative instead of just the fourth derivative? Okay, so that's the Lagrange error bound. So now we just need to find these values. For x, you're going to plug in where you're approximating it at. So where are we approximating it at? 0.1. So you're going to plug that in for x. And now we're going to find the maximum of the fourth derivative. For z between those values. What was our third derivative? Negative cosine. What's our fourth derivative? Sine. So we're going to find the maximum of sine for some z in between this region, 0 to 0.1. Well, what's the maximum of sine always? 1, right? Sine will never get above 1, right? So if we're between 0 and 0.1, sine will be, that'll be 1. So we're going to use 1 for the maximum because sine is always less than 1. So it doesn't matter, for this one it really doesn't matter that z is between 0 and 0.1. It could be between 5 and 10, and the maximum of sine will still always be 1. Okay?
So it doesn't have to be the interval in between 0 and 0.1, it just has to be the maximum value of sine.
It has to, but like sine is going to be maxed out by 1 over all real numbers, right? So whether you're between 0 and 0.1 or that. Does that make sense? Sometimes we might need to actually pay attention to what the interval is because the function might not be maximized by just 1.
So you're finding the maximum of the derivative between 0 and 0.1?
Yeah.
Okay.
Or using a maximum value, which like in this case, we know the maximum has to be, we don't know what the exact maximum is of sine over that interval, right? But we do know sine can't be bigger than 1. So we're using that. Does that make sense? If you had a graph and a calculator, you could probably find the exact maximum of that interval 0 to 0.1, and you could use that, right? Okay, so then this value, when we calculate this, is going to be 0.0000416. So our remainder, or our error, is going to be less than that. This is our max error, or our Lagrange error bound. So if you find the actual, if you were to subtract, if you actually find sine of 0.1 and you type it into your calculator and you subtract this from our approximation, it's going to be guaranteed to be less than this value. And you could actually do that and see it's less than that. So this is a good bound that we found. Okay? So that's a Lagrange error bound. Let's do another example to help you kind of get familiar with what this looks like. So this next example says the function has derivatives of all orders. That just means the derivative exists forever. Let Pn be the nth degree Taylor polynomial for f at x equals 1. Okay? We're going to show that f of 1/2 minus p3 of 1/2 is less than 1/12. So this right here, when we say the Taylor polynomial at x equals 1, that means the center is 1. So we're centering our Taylor polynomial at 1. We're going to do a third degree Taylor polynomial again, and we're going to approximate f at 1/2. If I plug 1/2 into f and plug 1/2 into my Taylor polynomial, subtract those, that's your error, right? So we're going to show that the error is less than 1/2. So we know the f of 1/2 minus the Taylor polynomial of degree 3 at 1/2 is guaranteed to be, that's going to be your remainder at 1/2. And this remainder, by Taylor's theorem, is going to be less than or equal to, if we're doing third degree Taylor polynomial again, which term are we going to be looking at here? Fourth again, right? I didn't get super creative here. Didn't do the fourth or fifth, right? Same thing, we're going to be looking at the fourth again. So we're going to look at the maximum of the fourth derivative for some value z here, our z is between our center. What's our center? 1. And where are we approximating our function value at? 1/2, right? We're plugging that in there. So here z is between 1/2 and 1. Divided by 4 factorial times x minus the center, which our center is 1 to the 4th power. Now we can go ahead and plug in. What do I plug in here for x? What number goes in for x? 1's the center, so that's already in here. X is where you're approximating it at. So what are we approximating it at? 1/2. So you can go ahead and replace that x with 1/2 instead of having to rewrite it all. And so now let's find the maximum of the 4th derivative for z between 1/2 and 1. So we don't have an equation for the 4th derivative, or for our f, but what do we have? What did they give us? The graph of what? What is this the graph of? What does that say right there? This is the 4th derivative, right? So we need a maximum value for z between 1/2 and 1. So somewhere in here. Z can be anywhere in here. So if we had an equation for this and a calculator, you could probably find that exact maximum, but we don't. So what would be a safe maximum value to pick? I don't know about 25. That's a little questionable. I think 30 would be fair, right? We definitely know. I mean, anything less than 30, who knows if that's actually maybe 20, maybe 29. You could maybe get away with 29, right? Pretty sure this doesn't go up to 29. But 30 would definitely be a safe. So use that as your maximum. So this will be negative 1/2 to the 4th. And that value will be 5/64. And we're trying to show that our approximation is less than 1/12. Is this less than 1/12? Yep, that is less than 1/12. So we showed it. So our Lagrange error bound is less than 1/12. We're going to do one more example together, and then the last example, we don't see those all the time, and I knew we wouldn't have time for it, so I'm just going to include that example in the video when I post it for you to check out, okay? So one more example here. It says find the 3rd degree Taylor polynomial for e to the x. It's not hard to do, but because we're a little short on time today, I'm just going to show you what that is. So if f of x is e to the x, we want a 3rd degree Taylor polynomial. I'm into 3rd degree today. Centered at 0. Okay? So if our center is 0 and f of x is e to the x, then a 3rd degree Taylor polynomial, I'm going to go ahead and give it to you. It's pretty easy to come up with, but we'll just write it out. It will be plus 1 plus x squared over 2 factorial plus x cubed over 3 factorial. Now, the derivatives are pretty easy here because if f is e, what value should we be plugging into f in all our derivatives for the Taylor polynomial? Our center, which is what? 0. What's e to the 0? 1. Yeah, good. 1. What's the derivative of e to the x? What's e to the x at 0? 1. So what will be the second derivative at 0? 1. What will be the third derivative at 0? 1. So all of these derivatives, right, are all 1, right? And then it's x minus the center, but what's our center? 0, so it's just x minus 0 squared, right? Divided by 2 factorial. Oh, sorry, there should be an x in here. I lost my x. Boop, boop. Sorry, there's a missing x there. So now, if we plug this into... We want to approximate e to the x at 1. So we're going to do e of 1. To approximate e to the 1, we're going to plug 1 into our 3rd degree Taylor polynomial. And if you plug that in, you will get 8/3. If you plug 1 in here, you'll get 8/3. Okay? So that's an approximation. Now that is going to be not perfect, and so we want to give a range of values for what the actual value could be. So let's find the maximum value of our error when we're approximating it at 1. So that'll be less than or equal to the maximum of the fourth derivative, again, because we're on our third degree Taylor polynomial, divide by 4 factorial. We're approximating at 1. Our center is 0. Our z is between 0 and 1 because we're approximating at 0 and our center is 0. So the maximum value here for the interval 0 to 1 will be whatever e is at 1. E to the 1, which is about 2.7. So let's round up a little bit, give ourselves some leeway, and let's use 3. So 3 over 4 factorial, 1 minus 0 to the 4th will be 1/8. So if you want to give a range of values for e to the 1, it will be less than 8/3 plus 1/8 and greater than 8/3 minus 1/8. Okay? That'll give us a range. So just to backtrack here a little bit, when we took the maximum value here was 3, okay? That's because if f is e to the x, then f prime will be e to the x, f double prime will be e to the x, so f to the 4th is also e to the x. And our z is between 0 and 1. So on the graph of e to the x between 0 and 1, the maximum value will be at e to the 1. So the maximum of f to the 4th of e to the x for us will be e to the 1. And because we're approximating here and we want a maximum value, that's about 2.7. So we took 3 as our nice value to use. And what's cool is that if you write out these values as decimals here, you'll have 2.5416 and 2.7916, and e is very, very closely in between those, e to the 1, if you type that in your calculator. So that's pretty nice. So your Lagrange error bound is this guy on the end, and you just added and subtracted that from your approximation. Okay, so last example here. We want to find the smallest order Taylor polynomial centered at x equals 0, which will approximate e to the x minus 1 on the interval 0 to 3. So if we want to find